Welcome to G Fun Facts Online. Today, we are diving deep into a structural transformation of the global digital ecosystem that is happening right under our feet, or more accurately, deep within the fiber optic cables traversing our oceans and continents. We are currently facing a structural transformation of unprecedented scale. Fueled by the exponential rise of artificial intelligence, high-performance computing, the Internet of Things, and high-fidelity streaming, the sheer volume of data traversing the globe is pushing our existing telecommunications infrastructure to its absolute physical limits. For decades, standard optical fiber networks have valiantly borne the weight of this data explosion. But the looming shadow of a capacity crunch has forced the scientific community to look beyond traditional transmission methods. The solution to this existential bottleneck does not lie in simply laying millions of miles of new cable. Doing so would be economically and physically impossible on the scale required to meet future demand. Instead, the answer lies in fundamentally reimagining the nature of the light we shine through those very cables. Enter the photonic frequency comb. This is a microscopic marvel of optical engineering that is poised to multiplex the future of fiber optics. To understand how revolutionary this technology is, we have to travel back a bit. Originally, the frequency comb was developed as an ultra-precise optical ruler to measure fundamental physical constants in time. It was so groundbreaking that it won the 2005 Nobel Prize in Physics. Back then, it was a complex benchtop physics experiment. Today, it has transitioned into a chip-scale powerhouse known as the microcomb. By generating hundreds of perfectly spaced, intensely coherent wavelengths of light from a single laser source, micro-resonator-based frequency combs are currently dismantling the architectural limitations of modern data centers. They are not merely an iterative upgrade. They represent a paradigm shift, enabling petabit-per-second data transmission rates, slashing energy consumption, and unlocking the ultimate potential of silicon photonics. To truly understand the gravity of the capacity crunch and the limits of our current technology, we must first look at how modern data is transmitted. The entire backbone of the global internet relies on a technology called wavelength division multiplexing, often abbreviated as WDM. Think of a prism that splits white light into a rainbow. WDM essentially does the reverse for data transmission. In a WDM system, multiple independent streams of data are encoded onto different specific colors or wavelengths of laser light. These various colors are then combined and sent simultaneously down a single, incredibly thin glass optical fiber. Because each color travels independently without interfering with the others, the total data capacity of a single fiber is multiplied by the number of wavelengths it can carry. It is a brilliant system, but traditional WDM architectures are built on a brute force approach. For every single wavelength channel you want to use, you need a dedicated independent laser, typically a distributed feedback laser. If a network architect wants to transmit 100 channels to handle massive data loads, they physically need an array of 100 separate lasers. But it does not stop there. They also need 100 individual modulators to encode the data, and highly complex stabilization circuitry to prevent each of those 100 lasers from drifting off their precise color frequencies. This legacy architecture faces three severe, insurmountable walls. The first is the energy wall. Powering, cooling, and managing hundreds of distinct lasers per fiber link consumes massive amounts of electricity. As AI clusters demand increasingly massive optical interconnects to train large language models across thousands of graphics processing units, the thermal and power footprint of these vast laser arrays becomes completely unsustainable. The second wall is the space wall. Data center real estate is incredibly precious. Packaging dozens or hundreds of discrete lasers onto transceivers takes up valuable physical space. This directly limits the density of switch architectures and bottlenecks the overall computational layout. The third wall is the spectral inefficiency wall. Because individual lasers inevitably experience phase noise and slight wavelength drifts due to tiny temperature and current fluctuations, engineers cannot pack the color channels too closely together. They are forced to leave wideguard bands, which are essentially empty spectral buffer regions, between the channels to prevent crosstalk and data corruption. This wasted spectral space severely limits the absolute number of channels that can physically fit within the transmission bands of a standard silica fiber. This is where the physics of the frequency comb completely changes the game through a symphony of solitons. A photonic frequency comb elegantly dismantles all three of these walls. Instead of relying on hundreds of individual, power-hungry lasers, a frequency comb system uses a single, continuous wave pump laser. This single beam of light is coupled into a microscopic ring resonator. Imagine a microscopic racetrack for light, typically etched from advanced photonic materials like silicon nitride or lithium niobate. When the single color of pump light enters this microscopic resonator, it begins to circle the ring millions of times per second. Here's where the physics gets fascinating. Through a nonlinear optical phenomenon known as the Kerr effect, the incredibly intense light begins to interact with the material of the resonator itself. Normally, light passes through glass without altering the glass. But at these microscopic scales and extreme intensities, the refractive index of the resonator material actually changes in response to the light's intensity. This process is called self-phase modulation. As the light modifies the medium modifies the light, causing the single original wavelength to spawn new, equidistant wavelengths through a process known as four-wave mixing. Under the exact right conditions of carefully engineered chromatic dispersion and incredibly precise tuning, these newly generated wavelengths phase lock with one another. They form what physicists call dissipative Kerr solitons. A soliton is a magical entity in physics. It is a self-reinforcing wave packet that maintains its exact shape as it travels, resisting the natural urge to disperse. In the time domain, the output of this microresonator is an endless train of ultra-short, highly stable optical pulses. But in the frequency domain, it appears as a comb. Imagine a literal comb you use for your hair. The spectrum consists of dozens or hundreds of perfectly sharp, perfectly spaced spectral lines or teeth. For the telecommunications industry, the implications of this microscopic comb are breathtaking. First, we achieve absolute equidistance. Because all the teeth of the comb are generated from a single microscopic cavity and phase-locked by the exact same fundamental physics of the Kerr effect, the frequency distance between each channel is mathematically perfect and permanently fixed. They physically cannot drift independently of one another. Second, this leads to zero guard bands. The immutable spacing of the comb lines means that the wasteful spectral guard bands required in traditional WDM can be entirely eliminated. Data channels can be packed incredibly densely, maximizing spectral efficiency and pushing data transmission right up to the theoretical mathematical limit, known as the Shannon limit. Third, we achieve massive consolidation. A single microchip, measuring just a few millimeters across, can replace hundreds of bulky, power-hungry individual lasers. It acts as a singular, elegant engine for massive parallel data transmission. But this is not just theoretical physics. Recent experimental breakthroughs have thrust the technology out of the realm of theory and straight into real-world record books, ushering in the petabit-per-second era. In a landmark, historic achievement by researchers at the Technical University of Denmark, Chalmers University of Technology, and Fujikura Limited, a single chip-scale microcomb ring resonator was used to achieve a mind-boggling data transmission rate of 1.84 petabits per second over a distance of 7.9 kilometers. Let us put that astronomical figure into perspective. 1.84 petabits per second is equivalent to the entire global internet bandwidth being transmitted through a single optical fiber simultaneously. It equates to downloading hundreds of millions of ultra-high-definition movies in a single second. This monumental feat was achieved by marrying the frequency comb with another cutting-edge technology known as space division multiplexing. The researchers utilized a custom-engineered optical fiber that, instead of a single light-carrying core, contained 37 distinct cores packed into a single strand. The single microcomb generated a stabilized dark pulse Kerr frequency comb. The light from this single comb was then perfectly split into 37 separate copies, one for each core. Across these distinct cores, the comb provided 223 perfectly spaced wavelength channels. Every single one of those channels was independently modulated with data. The end result was a staggering 8,228 distinct, parallel data streams, all running from a single microscopic light source. And theoretical analyses stemming from these experiments suggest that we have not yet hit the ceiling. By combining even more advanced microcomb arrays with massively parallel space and wavelength multiplexed systems, researchers predict that single-chip light sources could soon support capacities scaling up to 100 petabits per second. This fundamentally rewrites the entire engineering roadmap for high-capacity long-haul and submarine optical cable designs across the globe. However, while transmitting a petabit of data in a highly controlled, temperature-stabilized laboratory environment is a massive triumph, commercializing this technology for the bustling, heat-soaked, unpredictable environment of a hyperscale data center requires absolute mastery of manufacturing and integration. This is where the synthesis of frequency combs and silicon photonics becomes the absolute most important frontier in modern hardware engineering. Silicon photonics leverages the heavily established, highly scaled CMOS manufacturing infrastructure. These are the exact same multi-billion-dollar foundries that print the computer chips in your phone and laptop. Engineers use these facilities to etch microscopic optical components like waveguides, modulators, and multiplexers directly onto standard silicon wafers. However, there is a major biological quirk of silicon, so to speak. Silicon is notoriously poor at generating light due to its indirect band gap. Therefore, the ultimate holy grail for engineers has been to seamlessly integrate high-power, highly stable comb light sources directly onto the silicon chip itself, creating an architecture known as co-packaged optics. Recent breakthroughs, particularly those spearheaded by research teams at Columbia University, have pushed on-chip comb integration to spectacular new heights. By employing multimode laser diodes as a high-power optical source and utilizing advanced locking mechanisms, engineers have successfully stabilized and purified inherently unstable laser emissions directly on the chip itself. The light is reshaped through integrated silicon photonic structures, feeding into non-linear micro-resonators to produce high-power multi-wavelength frequency combs without the need for cumbersome external benchtop lasers. Furthermore, massive advances in hybrid integration are solving the historical challenges of this platform. Heterogeneous quantum dot mode locked lasers are now being bonded directly to the silicon substrate. This provides exceptional scalability, incredible high thermal tolerance, and massive efficiency improvements. Meanwhile, the specialized engineering of silicon nitride platforms has enabled the inclusion of integrated tunable dispersion compensation directly on the chip. To understand why this matters, you must know that a broad frequency comb experiences chromatic dispersion as it travels. Different colors of light actually travel at slightly different speeds as they traverse optical fiber, causing pulses to smear out over long distances. By pre-compensating for this dispersion natively on the microchip, engineers can achieve high-speed line rates, such as 50 gigabits per second per channel, over long distances, without needing complex, power-hungry digital signal processing at the receiver end. By placing the light source, the modulators, the dispersion compensators, and the receivers all onto a single monolithic die, silicon photonic frequency combs are poised to dramatically shrink the physical size of optical transceivers. For the booming artificial intelligence industry, where tens of thousands of GPUs must share terabytes of data with microseconds of latency, this tight system integration offers a path to optical interconnects that are exponentially faster and drastically more energy efficient. And that brings us to the environmental impact. The narrative of the frequency comb is not merely one of incredible speed. It is fundamentally a vital story of global sustainability. It is a thermodynamic revolution. The internet is a massive, often invisible engine of carbon emission. Data centers alone consume an estimated 1 to 2% of the total global electricity supply, a figure that is projected to skyrocket as generative AI and large language models proliferate across every sector of the economy. A highly significant portion of this immense energy is burned directly by the optical interconnects sending data between server racks and the subsequent massive air conditioning and liquid cooling systems required to manage the heat generated by thousands of discrete distributed feedback lasers. Replacing a standard transceiver's array of 100 traditional lasers with a single, highly efficient microcomb driven by a solitary pump laser drastically alters the entire thermodynamic profile of a data center. By encoding independent information channels onto the distinct colors of light generated by a single Kerr comb, hyperscale data centers can transition to massively parallel terabit-scale optical interconnects that operate on a mere fraction of the power. This green scaling is not just a nice bonus, it is absolutely vital. Without fundamentally more energy-efficient technologies, the exponential growth of computational power will literally be bottlenecked by the strict limits of municipal power grids and the immutable laws of thermal cooling physics. The integrated microcomb provides a crucial release valve for this immense pressure, ensuring that the exponential scaling of artificial intelligence computing can continue its upward trajectory without demanding a completely unsustainable environmental toll. But the magic of the frequency comb does not stop at telecommunications. While multiplexing data is currently the most lucrative commercial driver for photonic frequency combs, the ultra-precise nature of these optical rulers has triggered a massive renaissance across multiple distinct scientific and industrial domains. The perfect equidistance of their spectral lines makes them an absolutely unparalleled tool for any technology reliant on the manipulation or extremely precise measurement of light. Let us look at a few of these extraordinary ripple effects. First, consider astrophotonics and the hunt for exoplanets. In the realm of astrophysics, detecting Earth-like exoplanets requires observing the infinitesimal wobble of a distant star. This wobble is caused by the incredibly faint gravitational pull of orbiting planets. From Earth, this wobble manifests as an incredibly subtle Doppler shift in the star's light. To measure something so minuscule, telescopes require spectrographs calibrated to an absolute, unmoving standard. Enter the astrocomb. Utilizing gigahertz-spaced, passively stabilized frequency combs that often span from green to near-infrared wavelengths, astronomers can now calibrate their deep space instruments with a precision unmatched by traditional hollow cathode calibration lamps. These chip-scale astrocombs allow for the detection of radial velocity shifts down to mere centimeters per second, finally unlocking the ability to find smaller, Earth-sized, potentially habitable worlds scattered in the dark cosmos. Second is the incredibly important field of quantum communications and cryptography. As quantum computing matures, the threat to traditional internet encryption grows by the day. Quantum key distribution promises truly unbreakable cryptographic keys encoded in the fragile quantum states of individual photons. Recent proof-of-concept architectures have successfully demonstrated the seamless integration of quantum key distribution with dense wavelength division multiplexing using comb technology. By utilizing the pristine, phase-locked channels of a frequency comb, quantum-secure communications can actually be scaled and multiplexed over our existing global fiber optic infrastructures. This paves the way for a highly scalable, truly quantum-secure internet. Third, we have next-generation LiDAR. Autonomous vehicles, drones, and advanced topographical mapping systems heavily rely on light detection and ranging, or LiDAR, to create rapid 3D maps of their surroundings. Traditional LiDAR systems use mechanically sweeping parts that are bulky, slow, and highly prone to mechanical failure. Photonic frequency combs enable something far superior: frequency-modulated continuous wave LiDAR entirely on a chip. By utilizing the multiple coherent wavelengths of the comb, a single solid-state chip with absolutely no moving parts can emit massive parallel arrays of light beams. It can simultaneously measure both the exact distance and the instantaneous velocity of thousands of distinct points in real time, all with sub-millimeter precision. Fourth is high-resolution spectroscopy and chemical sensing. Because every chemical molecule absorbs light at a unique set of specific wavelengths, analyzing the light that passes through a gas or liquid can precisely reveal its chemical makeup. A technique called dual-comb spectroscopy utilizes two slightly detuned frequency combs. This allows for the ultra-rapid, ultra-high-resolution measurement of thousands of spectral absorption lines simultaneously. When integrated onto a compact silicon chip, this enables portable, highly accurate environmental sensors for real-time greenhouse gas monitoring, instant breath analysis for non-invasive medical diagnostics, and immediate chemical hazard detection in industrial environments. Finally, there is optical neuromorphic computing. The massively parallel nature of frequency combs is being harnessed to completely rethink the very nature of computation itself. In optical neuromorphic computing, forward-thinking researchers are using the distinct wavelength channels of a microcomb as individual photonic neurons or optical synapses. By passing these light channels through complex reconfigurable Mach-Zehnder interferometers etched directly into a silicon chip, linear algebraic operations, which form the foundational mathematics of modern machine learning, can be performed essentially at the speed of light. Even more incredibly, This optical computing process occurs with virtually zero power consumed during the actual computation process itself, as light perfectly passes through light. However, despite all of this staggering progress across so many fields, deploying chip-scale photonic frequency combs globally requires overcoming several highly stringent engineering challenges. The first major hurdle is conversion efficiency. When a single pump laser drives a micro-resonator to create a soliton comb, currently only a fraction of the pump light's initial power is successfully converted into the actual comb teeth. While recent advances in high-quality factor micro-resonators and dark-pulse soliton generation have drastically improved these metrics, ensuring that every single generated wavelength has the requisite signal-to-noise ratio for ultra-long-haul telecommunications without needing heavy, expensive optical amplification remains a highly active key area of study. The second massive hurdle is polarization and dispersion management. As mentioned earlier, standard optical fibers exhibit chromatic dispersion, which stretches and heavily distorts broad optical pulses over long distances. While on-chip tunable dispersion compensators are showing massive promise in the lab, maintaining the pristine integrity of hundreds of multiplexed channels across thousands of kilometers of transoceanic submarine cables requires exquisite, delicate management of both chromatic dispersion and complex nonlinear phase shifts. The third and perhaps most practical hurdle is foundry scalability. Transitioning from carefully curated hero experiments in university laboratories to reliable mass production requires extremely high-yield CMOS fabrication. The microscopic ring resonators must be etched with literal sub-nanometer precision. To understand how precise this is, even a single atom layer difference in the waveguide wall can completely alter the chromatic dispersion profile of the ring, entirely preventing the formation of stable optical solitons. The global semiconductor industry is actively investing hundreds of millions of dollars into new silicon nitride and thin-film lithium niobate fabrication nodes to standardize and scale the mass production of these highly complex photonic chips. In conclusion, we stand at the precipice of a fundamentally new era in optical communications and global technology. The relentless, completely insatiable demand for bandwidth, driven by an increasingly interconnected and artificially intelligent world, has forced our hand. It is demanding an evolution from the legacy discrete lasers of the past to the beautiful, mathematical symphony of the soliton. The photonic frequency comb is not merely a single upgraded component. It is an architectural revolution. By allowing us to multiplex hundreds of perfectly synchronized data channels from a single microscopic ring, it provides the master key to unlocking the impending capacity crunch. It promises a near future where petabit-per-second data streams flow effortlessly and invisibly across deep oceans, where massive hyperscale artificial intelligence data centers operate with drastically reduced power footprints, and where the boundaries of quantum communication, autonomous navigation, and astrophysics are continually and rapidly expanded. What began over 2 decades ago as a brilliant, isolated method to measure the fundamental tickings of the universe has now become the very heartbeat of its communication network. As research institutions and massive silicon foundries unite to perfect on-chip integration, the photonic frequency comb stands ready to illuminate the darkest fibers of our global infrastructure, multiplexing a faster, radically greener, and infinitely more connected future. Thank you for tuning in to G Fun Facts Online. Keep exploring the science that connects our world, and we will catch you in the next deep dive.